In this slide, we will check the MATLAB built-in functions for numerical integration. There are some built-in functions for the trapezoidal rule, and also it's called traps. And also we can find, so this is actually multiple segments or composite trapezoidal rule, and you can find the integral value for each segment using trapezoidal rule as well. Let's check the example of us. This is the fifth order example function, and let's use traps rule or traps function to get the numerical integration for this data. If you remember, this is an unevenly spaced data, but that's okay. These traps can be used for evenly spaced or uneven spaced data. No, doesn't matter. Let's write x's in one vector and y's, the function values, in one vector as well. And when you write the traps function by the x input values and y output values, they have to be in the same number, because the same number of points for both. When you use this, you will get the integration value. Z is the integrated value, 159, and we know that, when you calculate by your hand, you will get this result as well. You can compare it. And MATLAB also has another function, comptraps, and it calculates the areas in between each segment, or under each segment, let's say. So two vectors, x and y, hold the independent and dependent variables again here, x and y, and z gives a vector whose elements zk hold the integral from x1 to xk. So these in between these, you will get the results of them simply. In this slide, we have another example to use MATLAB built-in functions for integration. And we have a 70 kilogram parachutist, you can see here, with a drag coefficient of 12.5. And it will fall about 800 meters over a 20-second period if we analytically integrate the velocity function given by this. And this velocity function is given by this. So we want to use MATLAB trapezoidal rule. Instead of taking the integration of this, just use trapezoidal rule and traps function and comptraps function to estimate falling distance by numerical integration. With traps, we will get the entire position or the distance falling, and with comptraps, at each second, we will get the results. At each time change, we will get the integration results or the distances. Let's first generate data of inputs t and outputs vt by using this function. Let's say we want to get the t values for 0, 1, 2, 3, 4.37, 12, and 16 seconds. And these are the inputs of these. And when we calculate them and round them, we can get the velocity. This function is this actually. Then let's use traps function. For that, we have the x values are t's and y values, output values are v's, tv. And the MATLAB gives us 789.6. And this is closer to this analytical value, as you can see. But there is a small difference, of course. We can also estimate the cumulative distance at each time by comptrap z. So at each time change, how much distance it falls down, he or the parachutist falls down. When you write this comptrap z and t and v, it will give us at each time change, these are the increments, or you can see that it's falling down. That's why it's increasing from 0 to 789. And you can get all the data like this using comptrap z. These are pretty handy use of trapezoidal rule in MATLAB simply. For the same example, we can also plot the falling distance values for each segment or each second, each time. Here you can see the graph. The analytical integration was this when you take the integral of the velocity, and we simply write it here to get the analytical results. And these points are the numerical results, and the line is the analytical result from here. And t values are the same, but v values are calculated with comptrap z as the integration values, these points, the numerical results. Also, we have YA values, these are the analytical values, and YC values are the numerical values. We plot them. These are the analytical plot values, the line, and for T and YC, we have simply these points. And for the analytical value, TA is actually more, how can I say, more data we have for TA. With linspace, we generated more data to be able to get a line actually. And title, X label, Y label, and the legend, we can show them. And you can simply plot this after getting the analytical integration, and as well as the COMTRAP-Z for the numerical integration. That's simple, and you can simply implement this in MATLAB for any function as well. We can use MATLAB for multiple integrals too, and for that there are two options. Integral2 function is for double integration, in which we have x and y inputs. So it's used this way, a function, and the minimum and maximum values of x's and minimum and maximum values of y's, and it gives you the integration for two-dimensional function. Integral3 has the same idea, but with three inputs, x, y's, and z's. So it's for a function of three-dimensional function, let's say, with three inputs actually. If we want to solve example 21.9, which is the temperature calculation of this function, it is a double integration actually. We can use this integral 2 instead of using hand calculation. And when you write integral 2, the function is this, can be shown by at in MATLAB. Then the xmin, xmax are 0 and 8 for in the x direction, and 0 and 6 in y direction. And the MATLAB gives us this value, and we need to divide it by the 6 minus 0 and 8 minus 0 to get the mean, so that we can get the temperature. You can see that this is the same result as the true result, and we showed that in example 21.9 that the Simpson's rule is also giving the exact result. So probably this is using the Simpson's 1-3 rule to be able to get the exact result actually. And remember that the numerical result in example 21.9 for trapezoidal rule was 53. So this is with trapezoidal rule. And this is with Simpson's 1-3. This is also the same. So you can now use MATLAB to be able to get both one-dimensional integrals and multiple dimensional integrals. We have completed chapter 21, in which we learned about the closed form Newton-Cotes integration formulas, which were the trapezoidal rule with linear approximation of the function, Simpson's 1-3 rule and 3-8 rule, which are the second and third order polynomial approximation of the function respectively. And we also showed some two-dimensional integration, also MATLAB application of them. You can go back and listen those relevant slides or videos to be able to understand better. Also, you can go to chapter 21 in your book to have some further understanding of this. You can read that chapter in your book. Thank you very much for listening. See you in other classes.